Hi everyone, my name is Amitesh, and in this video we're going to introduce limits, as I've taught multiple times to students at Princeton University in freshman calculus classes. And we're going to start off by just getting a feel for what limits are, and then over time in future videos we're going to get into them in more detail. But I think this video really summarizes what they are and how to feel for them. So we're going to talk about three different functions first of all. So I'm going to start off by calling this limits. And we're going to talk about three different functions. The first function is going to be f of x equals to 1. The second function is going to be g of x equals to x over x. And the third function is going to be h of x is equal to x plus 1. Okay, so these are going to be three different functions that we're going to study. And what we're interested in is the following quantity, which I'm going to write it down all over here, is the limit as x approaches 0 of each of these functions. F of x, limit x goes to 0 of g of x, okay, and then limit x goes to 0 of h of x. Now I'll explain what this means. Okay, so first of all, what does this mean? So this means, what does f of x approach as x approaches 0? Okay, so as x gets closer and closer to 0, does the value of f of x get closer and closer to something? That's the question. Okay, so I'm going to write this out here. What does f of x approach as x approaches 0? What does f of x approach as x approaches 0? And it's going to be the same thing for the other functions. So what does g of x approach as x approaches 0? And what does h of x approach as x approaches 0? Okay, so that's what we're going to try to study. And these examples are kind of illustrative of an important point with limits. Is initially you sort of think it should just be the value of the function at 0. So for example, if you start off with f of x equals to 1, well, f of x is always equal to 1. It's a constant function. So as x approaches 0, it doesn't matter as x approaches anything really, but whatever x is, f of x is 1. So in particular, we can say that this limit x goes to 0 of f of x is just going to be 1. We can even draw the graph of the function. So the graph of the function, and I've overshot this a little bit because I want to draw the graphs of g and h too, but the graph of the function f of x is just going to equal to the following. It's just going to be a constant horizontal line. Okay, so we can write it as, I'm going to put this in blue, it's just going to be a line, and this line is going to be the line y equals 1. So it's just the value of the function is always 1. So that's the graph of f of x. So as x approaches 0, the value of f is approaching 1. Okay, so there's nothing to that. So we say that this limit is going to equal to 1. Okay, that's limit number 1. Now limit number 2 is a bit more interesting, because what happens with limit number 2 here is g of x equals x over x, is that g of 0 is undefined. Okay, 0 is not in the domain of g, because you cannot divide by 0. Okay, you cannot make sense of 0 over 0. There is no answer, because whatever 0 over 0 is, right, like if you try to make sense of 0 over 0, I'll just kind of briefly explain this here. Whatever number you say it is, well, if you multiply that number with 0, you should get 0. But any number satisfies that property. 5 could be 5 because 5 times 0 is 0. Could be 3 because 3 times 0 is 0. Just like, for example, 10 over 5 is 2 because 2 times 5 is 10. There is no one answer for 0 over 0 because anything times 0 is 0, so it can be anything. So therefore we say it's undefined. Okay, so 0 over 0 is undefined, so that's not in the domain of g. But what we can do is, we can still find the limit, and this is kind of the point of limits, is when you can't evaluate the function at a point, what should it be somehow? Okay, so let's think about g. You must have already looked at this function and said, isn't this just f? Isn't this just f of x, right? I mean, x over x and x cancel, it's just 1, right? So the answer is almost yes, but not quite. Basically, as long as x is not 0, it is f of x. Okay, so we can write this here, that g of x is equal to f of x, so this is equal to 1, so I can sort of maybe just remove the h for now just to create some space, but we can sort of say that g of x is equal to x over x, which is equal to 1, which is equal to f of x, if x is not equal to 0. Okay, so if x is not equal to 0, then they are equal. But at 0, g is not defined. Okay, the domain of g is all non-zero real numbers. So what we can do here is we can just draw this graph. And how do we draw the graph of g? So this is an interesting point. We don't just draw a vertical line like we did for f, because it's not really f. You know, it's not equal to f if x is not 0, but it is almost equal to f. So what we can do is we can draw this line. It's y equals 1. And what we do is we put a hole here. Okay, this is what we call a hole. Now, a hole will have a formal terminology as we keep exploring this subject. But basically what it means is that it's not defined at 0. Okay, the graph doesn't have a point at 0, 1. Okay, so we say this is a hole at 0, 1. Just to say that 0, 1 doesn't actually exist on the graph, unlike in the case of f of x. Now what is interesting is even though that's the case, you can still find the limit of g as x approaches 0. So what you can do is you can say that, and we can sort of, maybe I'll erase this here. Limit x, how do we actually verify this? Well, think about it visually first. As x approaches 0, but x is not quite 0, g of x is just 1. It's just f of x. So it doesn't really matter for the limit what the function is at the point, just what it is near the point. As you approach the point, what does it become? And so here it's still true that the limit as x goes to 0 of g of x, we can sort of write this. It's going to be the limit as x goes to 0 of x over x, which is equal to the limit as x goes to 0 of 1, because you can just sort of cancel off the x's, because it's the limit. It's not at 0. Okay, this is a point that keeps coming up conceptually, so I'm emphasizing it. It's not what happens at 0. So as long as x is near 0 but not at 0, it's going to be x over x is just going to be 1. And so then what you can say is this limit is just going to be 1. So this is the formal justification for what we see visually. And this may all seem very obvious, but I'm just highlighting the conceptual points first of all of what the limit is doing, which is what the function approaches as x approaches the point. Okay, so we've got that. And the next example I'm going to do, which is the final example, is we're going to look at the example of h of x. So here, let's just erase f. So for h of x, we recall that h of x was x plus 1. And this will also illustrate another important point of limits. So limit x approaches 0 of h of x. So maybe I can sort of say that h of x was equal to x plus 1. So this is just going to equal to limit x goes to 0 of x plus 1, right? And the idea here is that in this case, you can sort of just figure out, well, what does x plus 1 approach as x approaches 0 without even drawing the graph? Let's just think about that as x kind of gets closer and closer to 0, right? For example, if x is equal to, let's sort of just draw a table if you like. If x is equal to 0.1, then you're going to get x plus 1 is going to equal to 1.1. As x is equal to 0.01, you're going to get x plus 1 equals 1.01. You know, you keep on going, and even from the other side too, you know, because you can approach 0 from two different sides. You can approach 0 from the right or from the left on the number line. So if you approach 0 from the left and you say that x is a negative number that's on the left on the number line, x is equal to negative 0.1, you're going to get x plus 1 is equal to 0.9. And then as x is equal to negative 0.01, you're going to get x plus 1 is going to equal to 0.99, right? You can keep going. It doesn't matter. As x gets closer and closer to 0, your x plus 1 is going to approach 1. Okay, so conceptually here, all we're doing is just plugging in x equals 0 and saying that the limit is just going to be 0 plus 1, which is 1. This is an example of limits that is actually in some sense the most typical with natural functions, where the value of the function as x approaches 0 is just going to be the value of the function at 0. Okay, it's just going to be literally plug in 0 into this answer. But in classes, you know, at university, people don't like to give such easy problems, so they're going to give tougher problems where you can't just plug in. And generally speaking, you have things like this, where if you plug in x equals 0, you get something that's undefined. So you actually have to do some manipulation to understand what the function is near 0. Okay, so that's going to be a big focus on this in this class in general, is to understand those kinds of examples. But here we can sort of plug in and work out the limit is just 1. Okay, so now I'm going to do one more example, and I'm going to end the video after this because this is just designed to be an introduction. And this example is going to be similar to the ones we just considered, but I sort of brought up this point of approaching from the left to the right. Okay, so it's very important that actually there could be different answers on both sides. And this is the idea of left hand and right hand limits. So let's kind of just give an example which explains this very clearly. And I'm going to write out the following function. So I'm going to write out the function, let's just write out limit. Before I put the limit, let me just say what the function is. So let's call it f again. So f of x is going to equal to x over the absolute value of x. Okay, that's going to be our function. Now, it looks like a perfectly interesting function. The first thing we are going to do is we're going to ask the question, what is the limit as x approaches 0 of f of x? Okay, so we can't really do this just by plugging in x equals 0, because if you do that, you get 0 over 0, right? So you're trying to sort of work this limit out. You sort of say this is limit x goes to 0 of x over absolute value x, which is just going to equal to limit x goes to 0 of 0 over 0. That doesn't really work, okay? You can't do that. So let's kind of think about it a bit differently. What we want to think about is what is f of x as x approaches 0 but near 0, okay? And when you see the absolute value, this is kind of throwing in the absolute value in there, but I've done videos on that too, so please check them out. Links are in the description. And please like and subscribe, if you've watched so far. It means a lot. It really helps disseminate my videos to lots of different people. But let's kind of dive into the absolute value. So the absolute value is just going to equal to the following. If we think about it, it depends on whether x is positive or negative, right? So if you try to sort of understand, whenever you see the absolute value, try to split it up into cases, okay? When x is positive, we have some answer. When x is negative, we have some answer. So the absolute value of x is going to equal to x if x is at least 0. The absolute value of a number is its distance to 0 on the number line. That's the conceptual way of looking at it. So when x is at least 0, the distance is just x, because the distance has to be non-negative. But when x is less than 0, the absolute value is going to be minus x, because for a negative number like negative 5, its distance to 0 is positive 5. So you have to take the negative of negative 5, which is positive 5, to get the distance. The absolute value makes every number, from whatever sign it is, it makes the sign a positive sign. So here we have this. So now what we can do is we can write x over absolute value x. X over absolute value x, if x is at least 0, it's going to be 1, right? So if x over absolute value x is equal to x over x, so I'm going to write this in 2 steps. It's equal to x over x, which is equal to 1 if x is greater than 0, right? So if x is greater than 0 but not equal to 0, because we can't take 0 over 0, and then it's going to equal to minus x, or x over minus x, which is the same thing, but I'll just do it in 2 steps. It's going to equal to x over minus x, which is equal to negative 1 if x is less than 0. And I'll just throw in it's undefined if x is equal to 0. Okay, so we've got all that down. Now, you kind of can now see that, first of all, the limit doesn't really exist. So what I've just erased on the board is the limit as x goes to 0 of f of x is what does f of x approach as x approaches 0. Now, the thing is that as x approaches 0 from the right, we can even draw the graph if you want to be visual, which I think helps, but you can also do it symbolically, and it's really good in math to think about things in 2 different ways. But here what happens is, as x is greater than 0, so x is on the right side of 0, the graph of the function looks like y equals to 1. Right? It's just the value 1 for the function if x is greater than 0. But if x is less than 0, then what happens is you get the value y equals to negative 1. And when x is equal to 0, it's undefined. So what you would do here is you just put 2 holes there, if you like. So here I don't call them holes somehow, because in the previous case what happens is when you had the graph of x over x, it kind of just didn't exist at that point, but there wasn't any break in the graph. So it's kind of like you just poked a hole in the graph. Here you've kind of broken the graph up. You've kind of gone y equals minus 1 and then you jump to 1. Okay, you jump in your y value. This is what is called a jump discontinuity. Okay, so again, these are terms we're going to study in a lot of detail in the future, so don't worry about them too much, but I'm just going to kind of casually introduce them to you at the moment. This is called a jump discontinuity at x equals to 0. But to get to the point of the limit, we would say in this case that unfortunately, or not, doesn't really matter whether it's fortunate or unfortunate, but you would say that the limit as x goes to 0 of f of x does not exist. Okay, so we would say that limit x goes to 0 of f of x does not exist. Okay, does not exist, which you can also say as d and e. Okay, sometimes people write this as d and e. The reason is that f of x doesn't approach anything as x approaches 0. From the right it approaches 1, but from the left it approaches minus 1. However, you can still define what are called the right hand and left hand limits, and that gives you more subtle information than just this answer in this example, for example, because it explains to us what's actually going on. And what's actually going on, so we can kind of erase this here. So the right hand limit, which people denote, so I'm going to write this here, the right hand limit, so the right hand limit is basically going to be limit x goes to, so I'm going to write this, limit x goes to 0 plus of f of x. So this plus means what does f of x approach as x approaches 0 from the right? The plus is saying positive, okay? It's like on the number line, positive is to the right, negative is to the left. So here that's what the right hand limit is. This is what f of x approaches, as x approaches 0 and x is greater than 0. Okay, so greater than 0 means x is to the right of 0. So what does f of x approach as x approaches 0 and x is greater than 0? It approaches 1. So here we would say the right hand limit is 1. And similarly, the left hand limit, so you can kind of erase this here. The left hand limit is, you can see it from both the algebra and the picture, right? So the left hand limit is just going to be, so I'll say left hand limit is just the same thing, but it's going to be denoted by a negative sign in the limit. So limit x approaches 0 from the left of f of x. Okay, so that's going to equal to the left hand limit. This is going to equal to negative 1. It is what f of x approaches as x approaches 0, but x is less than 0. Okay, that's what the left hand limit is indicating. Okay, so here we've got the right hand limit and the left hand limit are different. This is an example where the limit does not exist. We call it a jump discontinuity. And I'm going to end the video there and just kind of give you a feel. These are just some basic examples, but the point is to give you a feeling for what's going on. We're trying to understand when functions aren't really defined at a point. To get an idea of the limit is to feel for what they kind of are near the point. That's the next best thing we can do. So that is the point of limits. And in general, you can do this for any function. So I'm going to sort of write this out. You can do it as limit x goes to a of f of x is just going to be what f of x approaches as x approaches a. So this is the general limit for any function f. It doesn't have to be this function. Okay, it can be any function. It's just basically what f of x approaches as x approaches a. And you can also study right hand limit and left hand limits, okay, as x approaches a. You can also study right hand limits, which is going to be limit x goes to a plus of f of x, and the left hand limit, limit x goes to a minus of f of x. Okay, so we'll do that in the future videos. Thank you so much for watching. I hope you love this video on limits. This is as I've taught at Princeton University multiple times in freshman calculus, and it's an important topic just to get a feel for conceptually, so then you can build on that with very tricky problems. We're going to go through more problems. We're going to talk about exam problems as they appeared at Princeton, homework problems, etc. So please subscribe, like my video. If you enjoyed it, please subscribe for more content. And to really help disseminate my videos, I want math education to be free and accessible to everyone in the world, not just those in schools or universities, but everyone can learn, enjoy, and benefit from the material here. And that's my ultimate goal. By liking and subscribing, you really help me achieve that goal. So I wish you all the best. I'm super excited to see you soon in the next video. Drop me a comment down below. I'd love to read them, and I'll definitely do my best to reply to as many as possible. So see you soon.